Hi, my name is Max Green, and I'll be presenting our paper on model-based approximate optimal feedback control of a hypersonic vehicle. First, here's a general outline of the talk. It starts with an introduction to hypersonic vehicle dynamics in general. I'll introduce the nominal linear parameter varying dynamical model. Next, I will introduce the switched approximate dynamic programming-based controller. I will briefly cover the stability analysis in this video, and finally I will conclude with some simulation results. On the right are the flight dynamics for the hypersonic vehicle. We have some very familiar looking dynamics, and one really important thing to note is this bottom equation, which represents the structural dynamical modes of the aircraft, which in turn affects the dynamical performance of the rest of the aircraft. So generally in hypersonic vehicle control, these structural dynamics are included because they're very crucial, and actually if they're ignored, they can result in overall system instability. So another important thing to notice is that these dynamics vary with respect to temperature. That is, as the hypersonic vehicle continues to fly, it will slowly increase in temperature, which affects the modulus of elasticity and therefore the structural modes of the aircraft, which in turn affect the rest of the dynamics of the hypersonic aircraft. I mentioned before that the dynamics are affected by temperature, but which dynamics specifically are altered? The structural modes affect how thrust, lift, and drag affect the aircraft as the flight vehicle heats up. Then similarly, like I said, the modulus of elasticity changes, which in turn affects the damping ratios and the natural frequency of the aircraft, zeta and omega, respectively. These complex hypersonic vehicle dynamics can be represented in a much simpler linearized control-defined form with an additional added disturbance term plus d. So in this specific approach, we assume that we also cannot directly measure all the internal states of the aircraft. Specifically, we don't assume that we can measure the structural dynamic states. So instead, we say that we can measure the forward velocity, angle of attack, pitch rate, altitude, pitch, and their respective differences from the linearized trim condition. While the parameter varying model is much simpler to deal with, the A and B matrices still vary with respect to the external system parameters rho, such as temperature. But we can actually further simplify this model to consider nominal A sub j and B sub j matrices that capture the behavior of A, B, and rho with an additional disturbance term at a given instance in time. And you can actually see these disturbances highlighted there at the bottom. So we have a set of nominal matrices plus a larger disturbance term. The approach we take in this result is to assume that the parameters, specifically vehicle temperature, is slowly time varying such that the nominal A sub j and B sub j matrices still capture the system dynamics and the changes caused by the time varying parameters at a given snapshot in time. Then as these parameters rho change slowly, then A sub j and B sub j are similarly switched or updated to reflect the new system dynamics. This approach raises a few questions that we answer in this publication. So if we're using all of these different nominal matrices and switching them in and out to reflect nominal dynamics, how can we determine the controller to use for each set of dynamics? Well, our inspiration here comes from traditional gain schedule based approaches in which the flight envelope is divided up and an optimal control policy is determined for each segment of the flight envelope. And a lookup table is used to determine what the optimal gain is within each of the segments. But this type of technique does not really scale well to this type of problem for hypersonic vehicles, because the added complexity here is that in addition to dividing up the flight envelope, each segment of the flight envelope also must account for significant temperature variation within each one. So in doing so, you end up with a very large number of segments to design optimal controllers for, and similarly, you wind up with a very large lookup table that you must use to store your optimal control policies. But what can we do about it? Well, we can assume that the linearized dynamics that are given, and instead of solving for all of the feedback gains offline, we can utilize approximate dynamic programming to solve the optimal control problems online, instead of solving a large number of them a priori. So in general, when designing an optimal control policy, we want to minimize the infinite horizon cost function j, which can be more generally embedded as the infinite horizon cost to go problem. Performing some manipulation on the infinite horizon cost to go yields the Hamilton-Jacobi-Bellman equation, or the HJB for short. HJB is a partial differential equation that is central to optimal control theory in general, and the solution is V star, the optimal control policy. Minimizing the HJB with respect to the control input actually yields the analytical optimal control policy. But the difficulty here is that to implement the analytical optimal control policy, you have to have knowledge of the optimal value function V star. So if we know V star, then we similarly know the optimal control policy. But unfortunately, this is a difficult thing to do because you can't actually solve the HAB analytically for every case. So what is done in approximate dynamic programming is that the value function is approximated with a neural network. So in the traditional case of approximate dynamic programming, the value function V star is parameterized as a single layer neural network, and then similarly that neural network representation is substituted into the analytical optimal control policy. But the difficulty is that we don't know the weights of the neural network a priori necessarily. So we develop some set of estimates, V hat and U hat, which represent the approximate value function and approximate optimal control policy respectively. And then we will update these weights WC hat and WA hat according to a metric, which is the Bellman error. And the Bellman error is a residual from the Hamilton-Jacobi-Bellman equation, and it is an indirect measure of the optimality or suboptimality of the control policy and value function approximations. Using delta as the regression metric, we want to alter the actor and critic weights appropriately so that delta decreases. So to be specific, the critic update law minimizes the Bellman error delta, the gamma update law modifies the least squares gain or the learning rate of the system, and the actor is updated so that it follows the set of critic weights. Applying approximate dynamic programming is well understood, but until recently, it had not been addressed from a switch systems perspective. And since we're switching different nominal matrices for this hypersonic vehicle, we're motivated to analyze this ADP-based controller from a switch systems perspective to obtain overall system stability. And as you can see on the right, when you have different dynamical systems or different controllers, we get different transient performance. And so the question that we're trying to analyze is, so while switching between these different types of controllers and different sets of dynamics, can we still maintain overall stability of the overall switched system? But why does switching add complexity to this problem? Why can't we just switch freely between the different feedback gains and learning policies? And this is because it's well known that switching between multiple stable subsystems may actually result in an overall system that's unstable. So we need to consider exactly how the system switches to show overall stability of the switch system. And this is theorem 1 of the paper. Theorem 1 of the paper says that there exists some minimum dwell time tau that each subsystem must satisfy before switching to the next subsystem. And in doing so, this guarantees UV stability of the overall switching sequence and guarantees convergence of the state vector y to a neighborhood of the origin. Now, to demonstrate the performance of this technique, we performed a simulation on a hypersonic vehicle at Mach 7.5 at 85,000 feet altitude. So to reflect the parameter variant dynamics, we used nominal matrices and injected nonlinear disturbances into the dynamics, which are further detailed within the paper. And then additionally, we also used a second order actuation model to make this vehicle performance more realistic. And here's a video of the switched ADP controller applied to the hypersonic missile simulation. So note that this video is actually played back in 2x speed. And like I said before, there are some very obvious additional disturbances injected into the system. So the perturbations, like you just saw, are extremely obvious and sped up ×2. While the video is a nice illustration of what the simulation does, what else can we learn from the simulation performance here? And we can see some of the individual states of the system on the right, but more importantly, do these states stay within a reasonable range of what they should be for a hypersonic vehicle at this flight condition? And the answer here is yes, according to some commonly referenced material in the hypersonic flight field. In this paper, we developed a switched approximate optimal control policy for the control of a hypersonic vehicle and demonstrated its performance in simulation. In the future, we want to extend this result further to consider more complex, nonlinear, and potentially partial differential equation-based models of hypersonic vehicles. Thanks for watching our talk.